In the unified coherence closure framework, unity is treated as more than just the integer 1. It is a structural condition, a marker that a mathematical relation has reached completion. The framework recognizes two distinct mathematical pathways that arrive at this condition. The first pathway reaches unity through exact phase closure and rotational inversion. This is the dimensional rotation seed, negative e to the power of I pi equals 1. Plotting this shows a vector rotating through a phase of pi to reach negative 1. Negating that result returns the system to its starting point. This closure is immediate. It involves no limiting processes, residual fractions, or asymptotic tails. Because the return to unity is exact and instantaneous, this equation serves as a primary seed. The second pathway arrives at unity through a process called asymptotic condensation. This is defined by the zeta terminal relation. The limit of the Riemann zeta function as s approaches infinity is 1. Unlike the rotational seed, this mechanism relies on the progressive suppression of infinite harmonic multiplicity. This comparison illustrates the two mechanisms side by side. On the left, the vector converges immediately through rotation. On the right, a limit operation tracks residual harmonic excess until it vanishes at infinity. The framework links these pathways through a unified terminal value. The limit of zeta of s equals negative e to the I pi, equaling 1. Both the suppression of harmonics and the completion of rotational phase resolve into the same state. To analyze the condensation pathway, we look at the internal structure of the Riemann zeta function for real s values greater than 1. The series begins with the number 1, followed by a sequence of diminishing fractions, 1 over 2 to the s, plus 1 over 3 to the s, and so on. Every term after the first represents the harmonic tail. The framework defines the sum of this tail as the residual harmonic excess, or epsilon sub s. This chart shows epsilon sub s as the excess value sitting above the invariant unit bar. As s approaches infinity, the limit drives this residual to 0, leaving only the first term. This identifies unity as the state reached once harmonic excess is extinguished. The next step is to find a geometric equivalent to this excess. Moving from harmonic series to geometry, we can analyze the curvature of a circle, specifically the value of pi. Pi is roughly 3.14159. The amount by which this value exceeds the integer 3 is defined here as curvature excess. The framework connects these fields through a unique inverse zeta value, the curvature excess zeta level, or kappa zeta pi. This alignment marks the point where harmonic and geometric properties overlap. It is governed by an exact equation, zeta of kappa zeta pi minus 1 equals pi minus 3. Kappa zeta pi has a calculated value of approximately 3.376996. At this specific level, the harmonic excess above unity perfectly matches the curvature excess of pi beyond 3. Locating this threshold allows us to bridge the behavior of the zeta ladder with geometric curvature. Using this alignment, we can perform an algebraic substitution. We rearrange the equation to define pi as zeta of kappa zeta pi plus 2. This flowchart substitutes pi into 9 minus 2 pi. Simplifying yields 5 minus 2 zeta of kappa zeta pi equals 9 minus 2 pi. On the right, this equals approximately 2.7168. For comparison, the constant e is roughly 2.7183. The harmonic geometric chain arrives at a value 0.0014 units away from e. Within this framework, the discrepancy is treated as a formal residual rather than an error in calculation. We can now address the exact quantitative difference between 9 minus 2 pi and the constant e. The framework defines this non-zero difference as the Euler gap, denoted by delta E. It is a deliberate measure of the space between two different mathematical regimes. The magnifying glass shows the gap of 0.001467 sitting between the geometric reduction and the constant E. The defining equation for this space is delta E equals E minus the quantity 9 minus 2 pi. This gap serves as a boundary marker, formalizing the relationship between harmonic reduction and exponential emergence. Delta E is the lawful residual that persists when these two mathematical systems are aligned. These relations are organized into a stratified architecture called law-layer condensation. This principle holds that distinct mathematical regimes do not need to be forced into an exact identity to maintain a coherent system. The pathways to unity form layers in a stack. The top layer, the primary seed, represents exact rotational closure. The middle layer, the derivative law, condenses harmonic multiplicity. The bottom layer, the reduction chain, links curvature excess to the residual gap at E. This leads to the finalized formulation: 5 minus 2 zeta of kappa zeta pi equals E minus delta E. In this view, harmonic resonance condenses into unity, while rotational phase restores it. The Euler gap marks the persistent boundary between the reduction of geometry and the emergence of the exponential.